Okay, we just described the basic geometry of this inductive structure, and we also performed the analysis using DC current source. Now, to make this problem a little bit more interesting, we will try to apply a time variant current source, a time variant current signal. So now the current source, the signal provided by the current source is a sinusoidal one, which can be represented by equation 5.88 as I sub 0 times cosine of omega times t. And as we seen in the previous slide, the magnetic field associated with the current source is referred as what? Here. I sub 0 divided by W, the width. So we can write up the fundamental term of the magnetic field using the expression of the current source. So you see here we have a subscript of 0, which means this magnetic field is the so-called fundamental term, which implies that we shall have higher order terms of magnetic field later on. Okay? Well, okay, for the time being, we have a time variant current source. Its magnitude is I sub 0 cosine omega t. Then substitute it into equation. In the previous magnetic field equation, we end up with I sub 0 times cosine omega t divided by W. So note that this one in the inside of the cosine function is omega, the angular frequency. The symbol on the outside is W, the width of the structure. And this is the so-called fundamental mode, the zeroth order magnetic field due to the presence of current. And to simplify our follow-up derivation, we shall now use the phasor representation, which we have introduced it in the previous semester. Now, the phasor expression. The phasor expression is a simplified representation of time-dependent signal without marking the time dependence in that expression. phasor representation 里头呢，它是时变讯号，但是你看不到时变讯号的痕迹，所以这个是大家约定俗成，大家讲好的，可以吗？所以虽然你看不到那个 time dependence， 但是它在那里而所谓的 phasor 呢，指的是专指特定正弦波频率的特定正弦波讯号，特定的正弦波频率的讯号。OK 所以它不是随随便便的时变讯号，而是特定频率的时变讯号那这个频率就是 omega。OK so the phasor representation is expressed as a bar over the parameter. So here you have a bar 一根杠杠在它上面所以它这边指的不是向量向量用粗体字代表，好不好所以你自己在写那个手写体的时候phasor 写成一根杠杠，然后向量电流算向量吗？算 OK 写成这样，好不好稍微把它分清楚了会比较方便一点。Right. And if you want to transform the phasor representation into the so-called instantaneous form, okay, so here in the middle is on the left hand side and the middle are instantaneous representation of the current signal. And it can be found with the phasor representation by multiply the phasor with exponential j omega t and taking the real part of that. Because as you know, exponential j omega t is what? It's actually cosine omega t plus j sine omega t. So if you taking the real part of an exponential signal, you get cosine of the you get a cosine of it, right? You get a cosine omega t. Okay, so we have a phasor representation. So in equation 5.90, it seems that it's not a time-dependent signal, but it is, okay? It is. So we just simply put I sub 0 on it, but you should know that it follows with cosine omega t, okay? It follows with cosine omega t, and we don't have to write it, okay, to simplify our derivation. So the current is I sub 0, well, it's actually a time variant signal. The magnetic field, which in fact pointing toward the y direction, is written as H sub y0 bar. Bar means it's the bar on the top indicates that it's a phasor signal, and it's equals to I sub 0 divided by W. I sub 0 over W. Okay, and now because I sub 0 is a time variant signal, so we can use Maxwell equation, the Faraday laws and Ampere's-Kirchhoff law, to find higher order electrical field and magnetic field. The first thing we can use is Faraday's law, okay? Faraday's law says the special derivative of Ex over Z, del Ex over del Z equals to the minus of time derivative of By sub 0. Well, the complete expression of this is right? But because we are operating on vectors, so the co-operation of E should end up in three equations. In y direction, x direction, and z direction. Oh, minus sign, okay, sorry. And for the z component, you actually have 偷看一下你知道我在画什么吧？哈，唉，所以 y 是 EZ 对 x 的微分减去 EX 对 z 的微分。Okay, so that should be the complete expression. Nah. 我错了什么东西啊？ 好像错了一个负号。All right. Okay, so this is kind of a simplified expression because we don't have EZ over del EZ over del X term. Because in this structure, you have HY term. And what is the electrical field within this structure? Well, we didn't tell you about that, but suppose you have electrical field. What direction can be for this electrical field? Horizontal one or vertical one? Vertical one. Why? Because it complies with the boundary condition of the top and bottom metal plate. So you can only have vertical electrical field, which is in the direction of axis, right? X, okay. Oh, okay, so it's actually pointing downward. It's pointing downward, okay. So the EX is actually in the minus X direction, okay? All right, so that's the reason why we don't have a negative side over here, because the EX is pointing downward. All right, so what does that mean? What is the physical interpretation of this derivative? Del EX over del Z. When under what condition can this be a non-zero value? Non-zero value. So H is in the Y direction. Okay. Y direction is pointing into the blackboard, and Z is pointing into the right-hand side. Now we know that electrical field is pointing downward here, EX. We will have EX here, EX here. Why? Because the current I is flowing from left to right on the top and right to left on the bottom. Okay? Which means there shall be a voltage difference to drive the current. Yeah. 我看看哪里写错了。这两个反过来啊。对，谢谢你。哦，所以我就不用我解释错误。OK， 这样就对了啊、哦，这样正负号就对了嘛，对不对 ？OK 好。哎，好吧。所以就是负的加 OK。啊，那因为我们没有 EZ component 嘛，我们只有 EX component， 所以就只简化成这样子 OK。So what is the significance of this? Under what condition can this be a non-zero value? Which means EX is a function of Z. X has EX value is different as you change on the Z direction. If you change your position on the Z direction. For example, And this is a reasonable result, because if you look to the very right of this structure, where it have EX component, 它可以有吗？最右边不行吗？为什么 ？Boundary condition 嘛，啊。So EX equals to 0 at the very right end. All right, so in fact, the voltage difference or the electrical field intensity are stronger at the opening and approaches to 0 at the right-hand side. In that case, the EX, the del EX over del Z shall be a non-zero value. And we can find out this by looking into the right-hand side, which is the time derivative of magnetic flux density. Then we can substitute result before as minus j omega mu times hy sub 0. The j omega part is the time dependence of this sinusoidal signal. In the phasor form, we use exponential j omega t to address the time dependence of the signal, which we didn't explicitly write in the text. We didn't explicitly write the exponential j omega t. But whenever you bump into the time derivative operator, you can put a j omega term on this to complete the time derivative 所以遇到时间微分就给它一个 j omega， 遇到2次就给它 j omega 的平方，好不好？就这样子。所以你的时间微分其实也不难处理。OK。All right, so is this the final result we want? No, we want a split expression for EX. So what we need to do is taking spatial integration about Z on both sides. If we take the spatial integration with respect to Z direction on the left-hand side, you end up with EX. Then what is the result of taking the spatial integration on the right-hand side? Because on the right-hand side, there is no dependent about Z. So the integration of this with respect to Z is simply this term, adding this term, right? With another constant, okay? That's what you have for performing integration. So you see EX equals to minus j omega mu times I sub 0 Z divided by W with plus C. So we want to determine what C value is. To do this, you will resort to the help of boundary condition. Should you look to the right or look to the left? We should look to the right, because here we are talking about electrical field intensity. The boundary condition on the right-hand side, which is a vertical metal plate, is very helpful here, because we know you have a vertical metal plate on the right-hand side. So at this position, you should have no EX electrical field, X component EX electrical field. So we can substitute the coordinate here, that is Z equal to 0, and you should end up with 0 as for the electrical field intensity. So to meet these conditions, to satisfy this condition, C must equal to 0. Okay? So we end up with this expression for the first order electrical field of this structure. Okay, so EX1 is the so-called quasi-static field. it's the result of a time variant signal within this structure. Okay, so it's produced by time variant magnetic field, time variant H. Okay, to be exact, is H0. So the zeroth order magnetic field turn, if it has time dependence, then it will produce first order electrical field turn, EX1, here. So looking into the composition of the EX1 turn, we know that it's proportional to frequency, right? The higher the signal frequency, the larger the electrical field. It's also a dependent of position Z. At Z equal to 0, EX1 equals to 0. For Z equals to minus L, which is the very left hand of the structure, if you substitute minus L into the for Z in this expression, you end up with equation 5.95, right? The total electrical field on the very left end of this structure is J omega mu L times I sub 0 divided by W. It's proportional to the frequency, and it's what? It's a dependent of the structural parameter, including the length, the width, the material property, mu, and of course, the current magnitude. The larger the current, the stronger the electrical field. On the other hand, the distribution of electrical field is not homogeneous across this structure. It becomes smaller and smaller as we move to the right. This is a linear variation, right? Z 的一次方嘛. That's the it's proportional to Z, okay? Not square of Z or cubic of Z. So it's a linear variation. Well, but it goes to 0 at the very right end. On the left end, the electrical field is strongest on the left hand. So what next? The voltage developed across the current source on the left end can be found by what? By taking the line integral of electrical field. So the line integral, the electrical field is pointing to the x direction. So you perform the line integral from A to B, from x equal to 0 to x equals to D. Okay, 从零积到 D. And the integration result is this. J omega mu times D L over W times I sub 0. This is the voltage built up at the left hand of this structure. Okay, so here we derive the expression for the voltage at the opening, which is J omega L times I sub 0. It's proportional to the current source. It's proportional to the frequency. It's also proportional to the inductance of this structure. Okay, so it depends on the size. So as you can see here, mu D L W is the expression for inductor, for parallel plate inductor expression. So we can substitute this with L. And if you want to increase the inductance of this structure, you can try to fill the structure with ferrite, with high permeability material. With this means you can increase the inductance as well. And so we found that this structure shall exhibit inductive property because we have not only the current, not only the magnetic field built up in this structure, we observe that there are voltage built up across the structure. We observe electrical field built up within this structure. So in the quasi-static, so this is the first order approximation in the time domain. So it's referred as the quasi-static approximation or quasi-static field analysis. So in the realm of circuit theory, you can adopt time variant signal by using inductance and capacitance to describe the phenomenon produced by time variant voltage or time variant current. All right. So the next thing is to determine the valid region, the valid limit for quasi-static approximation. To do this, we keep on applying the Maxwell equation. In the previous few slides, we used the Faraday's law, which addressed the spatial variation of electrical field and the time domain variation of the magnetic field. Now we will apply the Ampere-Circuitial law, which addresses the spatial variation of magnetic field and time domain variation of electrical field. In other words, we will try to see what can be produced with the time variant electrical field. Originally, we have time variant current, I0. You produce time variant magnetic field, HY0. And we have EX1, the time variant, the first order time variant electrical field. So the next thing is to find out what? The next thing is to find out HY2 using EX1. Okay? And in fact, you can end up with EX3. And of course, you have HY4, okay? Okay, due to the time limit, we will demonstrate the derivation of HY2 only. So use the Faraday's law, Ampere-Circuitial law. The curl of H equals to J plus this, and here we don't have current in the structure, so we use this. So actually, you should have HY del HY over del Z minus del HZ over del Y. However, we don't have HZ term, so we don't have to worry about that. We just use this relationship, which can be found using the complete expression for the Ampere-Circuitial law. So the right-hand side, you take the time derivative of EX. You simply add another j omega term. So you have minus j omega epsilon EX. And this is not a final result because we are troubled by the left-hand side. To get rid of the del Z operator, we should do what? We take integral with respect to the z direction on both sides. So we end up with hy2 equals to this here, because we need to perform integration with respect to z. So it's changed from z to the square. And we also need to add what? A 2, a 2 in the denominator. 这可以吧？这没问题吧？左边过来或者右边过去可以吧？所以把它寄回去嘛Okay, and you end up with another constant c double prime. And we, of course, need to determine the value of c double prime, which should be resolved using boundary condition. So now we should look into the left or into the right for solving the boundary condition for c double prime. 看左边看右边。我们在看电场的时候看右边嘛，所以现在磁场来看左边了。好 ，So what is the boundary condition of the right-hand side? The boundary condition tells you that the structure is connected with a constant current source. 你有用过 power? You have used power supplies before, right? So you can set up the power supply as constant voltage source or constant current source, right? So if you set up the constant current source, you set up, the current provided by the power supply is 1 amp. Then, under any condition, it's just 1 amp at the ends connector of the power supply, right? So, which means at this point, the current goes to the right and goes to the left should equals to 1 amp at any time. Or equals to 1 amp, anyhow. So, which means why? Because the magnetic field Hy2 is proportional to the induced current. It's proportional to the induced current. So you are free to produce currents anywhere inside this structure except at the very left end. Okay, so at the left end, the current, the higher order current should equals to 0. Otherwise, the boundary condition, that is, this is a constant current source, the condition cannot be met. Okay? So because the left end is a constant current source, the higher order current should be 0 at the left end. So therefore, substitute z equals to minus L, you should end up with 0 for Hy2 term, which produce the value for, you can derive the value for c double prime. Okay, so here is the complete expression for the Hy2 term. Okay, so that's the even higher order term, the second order term. And as you can see, it's a function of what? Frequency to the square. It's a function of position to the square. Okay, so for higher order term, what you can expect is it's becomes more and more volatile. Volatile 是什么意思？不平稳的啦，会抖来抖去的，会变得比较快的，叫 volatile. Becomes more volatile with respect to frequency and position. It changes more vigilantly. Okay, all right. Okay, you can do this. You can continue with this process to find out the third order term of the electrical field. By taking the similar procedure here, you have EX3, which is a function of, which is proportional to the cube of omega as well as the cube of position. The boundary condition to fix this is looking to the right, because at the very right end, you have no electrical field. And you can continue this to find out HY4 and EX5 as well. That's this, right? So this is the EX5 term. Looks pretty scary, right? Oh. And you can keep this on and on to find out following terms. In fact, so here it is. As long as the current source, the current is time variant. Now, the time derivative of the current source I is not 0, then you shall produce EX1 and followed by HY2, EX3, HY4, and EX5, so on and so forth. So if you do the collection of all the electrical field terms, EX1, EX3, EX5, you end up with this. 这个要回去自己看了哦，这个回去自己看清楚。You found out there some common term can be collected through the first, third, and fifth term of the electrical field. It looks like this. This is the common term. And here is the first order term, third order term, and fifth order term. And actually, it shall approximate the so-called Taylor series, tangent series. So which means the thing in the red box can be approximated analytically. 事实上它就是趋近 as a tangent function with the variable as omega times square root of mu times epsilon times L. Not 注意一下哦 ，L 在外面哦 ，L 在根号外面。我记得课本在这附近有错，有一个符号是把 L 写在根号里面，那个是错的哦。反正在里面，反正在外面就是了。OK。What is the significance of this parameter? Omega is the angular frequency. Omega 根号 mu epsilon 跟 L， 所以 L 是你的结构尺寸嘛，对不对？那个 F 字形的长度。Omega 是 2 pi over lambda， 这个是什么？西分之一。我卡住了。Omega 是 2 pi， 对不起，讲错了，对不起，写错。Omega 是 2 pi f 啊，贝塔才是2 pi over lambda 乘以西的负1等于2 pi f 乘上 fc 等于什么？等于2 pi over lambda 跟 L。好，所以你注意到重点在这里。所以那个变数是什么？跟什么有关系 ？The variable is proportional to the size of the structure and the size of the wavelengths. So you will become a significant number if L is comparable with wavelength lambda. Okay. All right, and so what about this part? This part is mu over epsilon is what? Eta, the characteristic impedance, right? So what can we do here? So here is the validation of a quasi-static approximation. So we see that under the first order approximation, we only take the first term. So without expressing the complete solution as a tangent function, we just use the first term over here. So, and this is true for small numbers. for small number. If alpha is much smaller than 1, which approaches to 0, tangent alpha will approaches to alpha. 这用你的那个计算机都可以按得出来啊，对不对？就用很小的角度取它的 tangent 值，就是那个角度。不要注意啊，不要用 degree 啊，要用 radian。你用 radian 去按的时候，就是这样的结果。So, which means, so under what condition alpha is much smaller than 1, or is the whole thing is alpha, right? So under what condition the tangent alpha equals to alpha condition can be met, which means L is much smaller than wavelengths. If the size of the structure is much smaller than wavelengths, then it shall meet the quasi-steady approximation requirement. You just need the EX1 term, first order approximation, to get the most significant answer, the most meaningful answer. Okay? So here is the derivation I put on the blackboard, which you can interpret it as L much smaller than 1/6 of the wavelengths. 好，所以这个是准进场的有效频率范围1/6个 lambda， 比1/6个 lambda 小很多啦。所以这其实又有一个判断的问题。那请问1/10个 lambda 有没有算小很多？有符合吗？这样有符合吗？好了，算符合了，好不好？好吧 ，OK 20/1个 lambda 有没有很小于1/6个 lambda？ 有啦，好不好？那就看你严不严苛啦，对不对？所以这算判断的问题了从数值上面来讲，1/10个 lambda 其实大概就 OK 了啦，就够接近了 ，all right？ So for frequency beyond equation 5.105 is valid, the input behavior of the structure is no longer essentially a single inductor, which means for higher frequency, when the size is comparable, when the circuit size is comparable to the wavelength, it will exhibit in capacitive property, as we can see in the following slide. So the conclusion for today's lecture is the circuit size must be much smaller than wavelengths so that the lump circuit assumption can be sustained, can be valid, which means you only need the zeroth order term and the first order term to represent the general behavior of the circuit components in this circuit. Okay? So the circuit size must be much smaller than the wavelengths. So let me show you the result for what beyond quasi-steady approximation. Just give you a quick. 我记得这边有这个东西啊。没有，好吧，没有就算了。在更后面啊，天啊！好了，最后这一个，这是一个电容啦。但是你会发现，电容到频率够高的时候，它会出现电感特性。这是平板电容哦，尾端开开的哦，尾端开开的。但是你只要给它一个时变讯号的话，你会发现到最后，它会出现，它除了是一个电容以外，频率够高的时候，它后面的东西都跑出来了。它会是一个电阻串电感，电感值的话会是那个结构的电感值的1/3，因为那个出来的那个电流只出现在左半部，右半部没有之类的。那假如是刚刚我们看到的电感结构，它会变成是 L 去串一个1/3的电容。但是你要频率够高才会看到这样的效果。好，我们